we talked about streaming a couple of times in like the previous conversation we just had. What is streaming, and why does it matter?
Well, first, thanks so much, Matt, for having me on. I've really enjoyed the two previous conversations, and excited to be on here. I think the best way to wrap your head around streaming is to contrast it with batch, and data moves, in either batch or streaming, in the sense that you either move data a few times a day, having batched up the data, or you send data points across your various systems as events happen. So one could imagine, for instance, when doing quarterly reporting, right? You just collect up all the things that happened that quarter. At the end of the quarter, then you do the processing, right? It's very different from, say, the sort of extreme example. The most early adopters of streaming technologies have always been financial use cases, where a new order comes in and you want to fulfill it immediately, or you do something at very, very low latencies. And what we've been seeing is that streaming has started to become, over several decades, and particularly in the past few years, much more broadly applicable beyond those small niche use cases, as more and more businesses and users benefit from lower latency answers to a variety of questions.
And it for anybody that follows the space, streaming has been something that people have been talking about for a while, but that seems to be accelerating now. So, for the last 2 or 3 years, a lot of people have been saying, oh, this is, 2018 is a big year of streaming, or 2019, 2020. It took a little longer than expected, it seems, but it seems to be getting there now. What are the drivers? Why is that accelerating so much as a key industry trend?
I definitely think there's a confluence of several factors. One is that the tools for moving the data around are starting to become more ubiquitous. Apache Kafka being the most widely adopted technology for moving data from point A to point B at very, very low latencies.
Jumping into this, do you want to talk about Kafka and like explain for like the non-technical part of this group, what's Kafka, why it's a big deal, and what it does?
Right. So Kafka is an open source technology, which is a message broker. So if you have various systems that are producing data, you have various other systems that are consuming data, you can put Kafka in the middle, and you can have the producers of data publish various feeds, and you can have consumers of data in a fairly decentralized fashion choose which feeds of data, or which topics, as they call them in Kafka, to subscribe to. And what this means is that you can sort of create this real-time clearinghouse infrastructure in your data in your company to allow various teams that may not even be coordinating or would otherwise, in the absence of a system like Kafka, have to essentially coordinate and talk to each other and figure out a way to move that data and closely integrate their systems. They don't actually have to do that coordination, and they can just sort of subscribe to those data feeds that are available and potentially come up with use cases that make use of that data in real time. You can imagine how this would happen in batch, right? So everybody at the end of the day would put all their data in a data lake, and then tomorrow anybody can pick up that data and do something useful with it. Kafka basically moves this into real time. And allows you to, within milliseconds, get access to data that has just been created by upstream services in your company. It has been, in my opinion, a key enabler of microservices. I think it's pretty difficult to build and operate a decentralized set of microservices without first adopting something like Kafka in your organization to just move the data between all of these various microservices.
Right. Now, where is there a need for a streaming database?
Right. So the biggest reason I would say is that today's analytics databases, while very sophisticated and very powerful, are fundamentally designed around the batch paradigm. So the best way to contrast this is a lot of batch workloads are very pull oriented. So you show up, you say, I've got this database and I wish to recompute or compute fresh a bunch of queries. And these queries can be very complicated. They can join, merge, many data sets, very, very large data sets and things like that. This paradigm doesn't really work in the streaming world where you may be getting, in aggregate, still very large data, very big data, to use the phrase, but every few milliseconds you get another row of data, right? So stopping everything and recomputing from scratch is not really a framework that scales to these lower and lower latencies, which is why fundamentally a lot of analytics databases today, including some of the more famous ones, they would prefer it if you would just batch up all your data over a few minutes and then rerun the computation, right? So they introduce latency because the paradigm in which they perform their computations is not suited for incremental recomputation. And it's really, another way we thought about describing Materialize was we're an incremental database, right? So we are suited for updating arbitrary queries, arbitrary answers, when the underlying data changes, even if that change is small or that change is happening at very, very high frequency. So, every few milliseconds, and in aggregate, hundreds of thousands or millions of updates per second.
And as you build Materialize, you chose to go the SQL route. Can you walk us through the thinking that led to this?
Yeah, so I think SQL it's incredibly underrated as a standard for describing computations and describing the queries that one executes over all these data sets. It's incredibly long-lived. It's 3-4 decades old. And if you think of many mature organizations, the corpus of SQL queries and analytics workflows that they've defined over decades is very, very rich, right? And so any pitch, I'm generally very skeptical where you can tell folks, you can have all these great new benefits of low latency or whatever it is, but you got to start all over from scratch, right? You have to throw everything out there and you got to rebuild everything in some new language. I think those efforts are largely doomed. SQL is also a great standard for interconnectivity. So you have all sorts of different tools. Any company that is any scale or even no scale at all usually is using a dozen or hundreds of tools. And these tools all talk to each other using standards like SQL. So a good example of this is a BI tool like Looker is pulling or is issuing queries to a data warehouse like Snowflake, which is pulling data from a source of truth database like CockroachDB, right? So you take these three, they're all able to speak to each other because they speak that common language of SQL. So the user who's moving the cursor and clicking some things in Looker, they may not even be writing any SQL query, or they may not even know SQL, but every click that they do on Looker is issuing under the hood various SQL queries that are being parsed and executed by the data warehouse like Snowflake. And so I think one of the most important things is to recognize that when selling or adopting new technology, you are working within a context of an ecosystem that is orders of magnitude larger than your tool. And SQL, I think, is the best example of that in the data space.
And where do you think SQL came back, right? There was this whole evolution over the last few years from traditional SQL databases, and then like the next bit was everybody was saying, well, it's all NoSQL, and then SQL came back. Like, what was the journey there?
Right. So that's a great it's a great case study. For those of us veterans who've been around for a while. I mean, a couple decades ago, I mean, SQL was done, right? There was this big movement of NoSQL and Hadoop saying, and the fundamental message there was that the data sets were growing so large and your SQL databases were never going to scale, and your SQL data, like if you wanted to process these ever-growing data sets, you had to throw everything out and you had to start over by using horizontally scalable technologies like NoSQL on the transactional side and Hadoop on the analytical side, right? And this obviously had some uptake. This had some adoption, but I would classify that as adoption among folks who could build and maintain, and we're starting in a fairly clean slate manner. So the tech companies, the first sort of, I guess the first and second waves of sort of web companies would adopt Hadoop, but by and large didn't really get to a lot of mainstream adoption. It was only when sort of you had this new SQL that came of vendors and technologies that came about that took those same, ultimately correct ideas of horizontal scalability, cloud native sort of architectures, but then packaged it up such that the interface was still this very same SQL that people were used to, that you really saw mainstream adoption across, not just Silicon Valley companies, but all across the world. And this is why I think ultimately, Snowflake is a fantastic example of, under the hood, they have a very modern microservice architecture, but it's all sort of very neatly wrapped up with the bow on top such that it looks like a SQL database, and that's much more attractive to folks who already have decades of SQL queries and analytics queries that fundamentally needs to be ported over and run in this cloud native fashion, but without throwing it all out.
Great. Let's dive into Materialize a bit more, with a bit more granularity. So it's based on an open source project called Timely Data Flow. What is that? What is the history there?
Right. So Materialize, despite being a relatively young company, we're a little over 2 years old, is based on close to a decade of stream processing research, primarily driven by my co-founder and Materialize's chief scientist, Frank McSherry. So Frank has done a lot of, he was an academic, he worked at Microsoft Research for a while, where he made several contributions to various parts of information theory, data privacy, and also big data computing. But he led a project to build a next generation stream processor, which he then developed as an open source project called Timely Data Flow that he had written in Rust, which back then was still a programming language that was under development in a sort of pre 1.0 state. I was a close follower of this technology because I was a PhD student at Penn in distributed systems, distributed computing, and it was sort of the first, what I would describe as the very first stream processor that could do everything that batch processors could do. Like in the sort of pre-Timely Data Flow world, there existed stream processors like Apache Storm, but they fundamentally posed a trade-off. They said, you can do some things in real time, you can do some things incrementally, but you can't do everything that you can do in batch, right? So you have to choose. Do you want to do complex computation or do you want low latency? And Timely Data Flow was the very first stream processing technology that said, everything you can do in batch, you can do in streaming, and you can do it in low latency. So it removed this trade-off aspect and made it sort of purely dominant as a technology. Timely Data Flow is the core technical base layer of Materialize. The way I would phrase it is, it's a little bit like it's the engine and Materialize is the car, right? Like and SQL is the same gear shift and accelerator and steering wheel that you could use, right? You can't fundamentally go to market, holding a very heavy, much more powerful engine. People still ultimately, at the end of the day, they're trying to buy a car. They're not trying to sort of hot rod, and there's a few people who have adopted timely data flow and are running in production. The hot rod enthusiast community in this analogy, but Materialize sort of wraps that up. That extremely scalable, extremely high performance streaming computation engine in a way that looks and feels very much like the SQL databases that people have been used to for 30, 40 years.
And so what are the pieces that you built on top then to help achieve that?
Yeah, so the Timely Data Flow project also includes this other part that called differential data flow, which builds reusable components that can be assembled and into these data flow graphs that are executed. But Materialize builds all of the SQL planning, the optimization, the integrations to tools like Kafka, the integrations to pull batch data from S3. Oftentimes, even when you do have streaming data, you often need to mix streaming and batch. That ends up being another challenge because, again, not everybody's throwing out all their batch data or their batch tools and technologies overnight and switching to streaming. Oftentimes, there's a long phase where you're dealing with both batch and streaming data in parallel. And the integrations, the SQL execution, and then finally, the tools that make it easy to operate and scale and deploy the system in the cloud.
Great. And you have a concept of Materialized Views, and I'm reading from my notes here some. It's a concept like an update trigger and update granularity. Do you want to dive into those and explain what?
Yeah, so Materialize, the reason we called the company Materialize is that what we really see happening is us delivering on a feature that hasn't really a long-standing database feature, the Materialize View, that hasn't really lived up to its potential or its promise. And the way to think about a Materialize View is. Let's imagine you're writing a query and you're rerunning it over and over again. And the data may change, the data may not change, right? So sometimes you're refreshing to see if that package is still in Memphis, right? That's a great example of a query that we're all been rerunning all the time. A Materialized View basically is a register to the database. I'm interested in the results of this query. Please recompute it for me so that it's fresh. Right. So when I come and ask for it, I want it to be top of mind for you. And if any of the underlying data has changed, please recompute the query at that point. So basically triggering the recomputation when an actually relevant update happens, rather than when I ask for it. Right. So if the database starts doing work when you ask the query, if it's a very large data set or it's a very complicated query, you may have to wait minutes or hours before you get the answer. But if it's already recomputed that answer when the data has changed, but by the time you come and ask for it, it's ready for you in milliseconds. So Materialized Views have been present in databases, as old as Oracle or SQL Server, but they've been very limited in the kinds of queries you could write and the kinds of Materialized Views we could write. And we really think Materialize, the product, is the first database that gives you, I don't want to say literally all the functionality, but sort of morally speaking, 99.9% of the functionality that you can write in a batch database.
And trigger and granularity, what does that mean?
In trigger means you are recomputing the result when the data changes, as opposed to, so this is, if the data may not have changed, you don't want to actually waste a lot of computation rerunning just to get the same answer, right? So the update triggers is important for both performance as well as efficiency. The update granularity is you actually want the capability to recompute efficiently when a single data point changes, rather than being incentivized to sort of accumulate a bunch of updates and batch them up together, because it's too prohibitively expensive to update your answer on just a single row changing.
Great. You just announced a partnership with DBT, and we had Tristan, the CEO of Fishtown Analytics, the company behind DBT, speak at this event. 2-3 months ago now. So curious, what does that do? What's the idea here?
So DBT is this amazing tool that is gaining a lot of adoption. DBT is the modeling layer for you to, the way I like to think about it, and Tristan may not like this, but I think of it as like GitHub for all of your SQL, right? It's like there is workflows, there's continuous integration, testing, there's processes that you want to have to stay sane when your company or has thousands or tens of thousands of lines of SQL just sort of spread across all, and with all of these interdependencies between this SQL query depends on this data set, which is computed by this SQL query, which depends on this data set, etc. That is where, in my view, most of the world is moving to in terms of writing and defining that SQL. And the bulk of that today is, of course, done on batch systems. And I think the thing that will truly unlock the potential of streaming is when, a company can go from batch to streaming by taking that existing SQL that's already been written and defined in these DBT models, and then sort of flip a switch and say, we're now moving all of this recomputation to a streaming pipeline without really having to rewrite that SQL, because DBT does a wonderful job sort of abstracting that away from the underlying execution engine in a way that the semantics are perfectly preserved. So I think it's until streaming gets to the same level of tooling, and a large part of that tooling is DBT, as existing batch systems, it will still remain a fairly niche technology.
Exciting. So what's next? What's on the roadmap for 2021?
Well, the biggest one next month is we're launching our cloud product, our fully hosted cloud product. This is I think this is definitely one of the top requested ways to use Materialize. Today, it's a source available, downloadable product, but particularly with database infrastructure, I think more and more users and customers wish to use a fully hosted cloud product rather than having to sort of own and operate infrastructure and hold a pager, right? In terms of the core features, we are working on tiered storage this year that we will launch. Tiered storage is basically the ability to store large historical data sets on very cheap storage like Amazon S3, such that you don't have to really think about separating out your historical data set. That just sort of happens behind the scenes. So live data is often stored on very expensive storage, and then you want to minimize and compact away. Let's just keep one day's worth of data on this expensive storage, and let's take the history of years and years of data and put them on tiered storage. That ends up creating a lot of organizational sort of complexity, operational complexity, and building that in natively to the product means that users will just define SQL, and the data that's relevant will stay sort of in local disk, and the data that is historical will sort of just magically disappear to tiered storage. Next year, we're building replication. This is for the more business critical use cases where you want, very, very high availability, very, very low downtime. You will want to run replicated instances of your database so that if one goes down, the other one can seamlessly take over.
Great, wonderful. All right, so we pretty much out of time for this event. I see a couple of questions which I think you covered during the discussion, like is Materialize a relational model like Oracle, NoSQL like Mongo, so a relational model. So let's call it a wrap. Thank you so much. Really appreciate it. That was fantastic and very, very educational. So thanks very much for coming by.